In this video, we are going to talk about compressions and stretching, vertical compression and stretching, and we're going to call those things dilations. So just like your eye dilates, your pupil dilates, and it can get bigger or smaller, these will be dilations like that. I'm going to use the Desmos graphing calculator again for this to help me with the graphing so that you can see the ordered pairs that are involved. Remember that we're not calculating the ordered pairs. We are just using the transformations that are here, or the parent function that we know and transforming it. So for example, in this first function, y equals 2x to the second, we're going to double all of the y values that are in our parent graph, and we see that this graph has been stretched vertically. It's stretched out like a rubber band, so it gets taller and it looks skinnier because it's growing faster in the same amount of horizontal distance. It's growing twice as fast each time. So instead of growing only 1, it grows 2 here. Instead of growing 4, it grows 8, and so on. Let's look at a vertical compression now instead, and I'll make this 1/6 out front. And we see that when that happens, we are going to grow slower vertically, so this makes the graph look shorter and wider, but it's really the shorter part that's going on right now, whereas the factor of 2 made it taller. The factor of 1/6, which is between 0 and 1, makes it shorter. And these are all fractions that you can calculate. That's 2/3, and that's 1/6. And again, 1/6 and 2/3. All right, let's try this now with a cubic function instead of a squaring function. And this is going to be 6x to the third. So we are going to have our parent graph in red here, and everything has been stretched by a value of 6. If I zoom out, you'll see this point way up here because 6 times that point that was there, that was 28. 8 times 6 is 48, is way up there. But we're going to stick into this little area here with negative, probably with the -1, 0, and 1, because we're not going to be able to graph 48 or -48 on our graph paper probably. And there it is. You can see the transformation that these points have been stretched, but 0 doesn't get stretched at all because 0 times anything is 0. Let's compress this now vertically by multiplying by 1/7. And again, you can calculate all these fractions if you would like to. This would be a -8/7. This would be a -1/7. This is 0, 1/7, and 8/7. But you can see that each of these values here, if I divided the y value by 7, then I'm going to get the new y value. It's a lot easier to do this on a calculator like this, or on your 83 or 84, than to manually have to divide numbers by 7 and try and plot it with the XY ordered pairs. In fact, the whole point of this problem is you don't like to divide by 7, but we can imagine compressing the graph by a factor of 7 and sketching the graph. It doesn't have to be perfect, but we can imagine cutting this in half by 1/7 and putting the point there, and imagine cutting this down so that it's divided by 7 or multiplied by 1/7 and putting the point right about there. And we can imagine this curve that we're going to get here from these characteristic points without actually having to calculate these decimals or these fractions exactly. Let's talk about another type of function now with the square root function. And that's going to change my characteristic points here. There we go. And that's going to change these characteristic points down here as well. Different types of graph have different characteristic points. So let's make this 5 times the square root of x. And you see now that it looks less obvious that it has the same shape because I've stretched it out so much. But I took this y value and multiplied it by 5 to get that y value. And this y value multiplied it by 5 to get that y value. And this y value multiplied it by 5 to get that y value. All the x values are staying the same. So that's really stretched out. It's growing really, really fast in comparison to the parent graph. Let's try now, not 5, but let's try 1/5. And that's going to make it grow a lot slower. Now the blue function is growing slower than the parent graph red function. So this 4/2, if I take 1/5 of 2, I'm going to get 0.4, and it's hard for me to click on that exactly, but it's there at, there it is, 4.4 and 0.4. And this is going to be 0.6. It's, again, hard to click on, but it's right there, 9.6. And then if I take 1/5 of that, that's 0.8. You see how that's growing. Again, you'd have to probably adjust your scale on your graph paper so that you could graph that, because you're not going to really be able to get distinct points that are easy to tell apart for 0, 0.2, 0.4, 0.8, so on. All right, let's try absolute value of x now. Get back to my characteristic values for that. And let's get back to the characteristic values here. And we're going to have a new function here that's going to be 2 times the absolute value of x. And center this. It's still an even function. It's still got this y-axis symmetry going on, but you can see that I've multiplied each of the parent graph y values by 2, and it has stretched it out like so. So blue function is like a rubber band that I've stretched from the red function, and everything is growing twice as fast. Let's try and make it grow slower now instead. And you're going to see here that this is a vertical compression. And we have, instead of 1, 1, we're going to have 1, 1/4. And 2 instead of 2, 2. We're going to have 2, 1/2. And the same thing over here. It's going to be reflected -1, 1/4, -2, 1/2. We're going to be staying there at 0, 0, and you see that it is shorter and it looks wider, but the key thing that's going on here is because this multiplier is between 0 and 1, that this is shorter. It's not growing as fast. It's only 1/4 of the y value for the same x value. All right, let's try and do one of these where we do all of it together. So I'm going to put in my parent graph of x squared here. I'm going to put in the function here, 3x plus 1 quantity squared minus 2. And I have shifted all of the x values to the left one, so let me do that here. That'll help you see the transformations that have happened. So my origin, or not my origin, my vertex is shifted from my origin, left 1 and down 2. And then instead of just going right 1 and up 1 from there, I'm going right 1 and up 3 because of the stretch of 3. So I have to multiply all of these y values here by 3 to figure out how much I need to grow for each step. So right 1 up 3, right 2 up 12. So right 2 up 12 will get me up there. Left 1 up 3. Left 2 up 12 will get me there. And that's my transformation. Let's answer this question over here now about the point on the graph. Very similar to last time. And it says that suppose that 2, 4 is on the graph of f of x, find the point that's guaranteed to be on the function. So we're leaving the x value alone, but we need to multiply the y value by 2, or I'm sorry, by 4. 4 times 4 is 16. So that guarantees the point 216 is going to be on the graph. Next time that we come back, we will talk about reflections. And these reflections will be about either the x-axis or the y-axis. We're going to do both types of reflections in the next video.